Somewhere right now, there is an asteroid drifting silently through the darkness of space. It has no name that most people would recognize. It has no flag planted on its surface. No one has ever touched it, photographed it up close, or even thought much about it. And yet, inside that unremarkable chunk of rock and metal, there is more gold than humanity has ever pulled out of the ground in all of recorded history. More platinum than has ever been refined, more nickel, more cobalt, more iron than any mine on Earth has ever produced. And it is just floating there, waiting. That idea, that kind of staggering, almost incomprehensible abundance, is what we are going to spend the next couple of hours exploring together. Tonight, or wherever you are as you listen to this, we are going on a journey. Not a rushed one, not a frantic one. This is a slow, deliberate, calm walk through one of the most extraordinary stories unfolding in human history. A story about money, ambition, science, survival, and the very future of our civilization, the space mining industry. A trillion-dollar frontier that right now barely exists, and yet may one day change everything about how we live. You might be wondering why you should care. After all, space feels far away. Asteroid mines feel like science fiction. When most of us think about our daily lives, we think about grocery prices, rent, gas, the weekend. Not platinum deposits on a rock orbiting the sun millions of miles away. But here is the thing. The materials locked inside those asteroids and other celestial bodies are already part of your daily life. The cobalt in your phone's battery, the gold in the circuit board of your laptop, the platinum in the catalytic converter of your car. These materials are already running out on Earth. Mines that took decades to develop are beginning to go dry, and demand, driven by electric vehicles, renewable energy, and billions of smartphones, is only rising. The collision between a finite Earth and an infinite demand is already happening. And the answer, some of the most brilliant minds on the planet now believe, is not to dig deeper into the ground. The answer is to look up. So tonight, we look up, we go slowly, we take our time, and we tell the story, from the very beginning, of how human beings are preparing to mine the stars. To understand where we are going, it helps to understand where we have been. Because this is not the first time in history that human beings have looked at an impossible frontier and said, there is treasure there, and we are going to get it. Let us go back, way back, to a time when the idea of sailing across an open ocean with no land in sight was considered by most people to be an act of madness. The year was 1492, and a navigator named Christopher Columbus set off from Spain with 3 ships and a dream of reaching Asia by sailing west. He did not find Asia. What he found instead changed the shape of the modern world. He found the Americas, a continent absolutely brimming with resources that the European powers had never imagined. Gold, silver, timber, agricultural land. The floodgates opened. Within decades, Spanish galleons were hauling tons of silver out of the mines of Potosi in modern-day Bolivia, so much silver that it caused inflation across Europe. The wealth of a new world was pouring into the old one. Then came the gold rushes. The California Gold Rush of 1848. The Australian Gold Rush a few years later. The Klondike Rush of 1896, which sent tens of thousands of people trudging through the frozen wilderness of the Yukon in search of a fortune. These events were not just economic moments. They were civilizational turning points. They built cities almost overnight. They drew populations across oceans and mountains. They created entire legal and political systems from scratch. The modern state of California, the world's 5th largest economy today, exists in large part because someone found gold flakes in a sawmill in 1848. The pattern, when you step back and look at it, is always the same. Someone discovers a resource in a place that seems unreachable. Everyone says it is impossible, too dangerous, too far. And then people go anyway, because the reward is too great to ignore. And in going, they build new roads, new technologies, new institutions, new ways of thinking. The frontier shapes the people who cross it, just as much as the people shape the frontier. Now look up. Look at the sky on a clear night and imagine it differently. Not as empty darkness, but as the richest minefield in the history of the human race. The asteroids alone, the millions of rocky and metallic bodies orbiting between Mars and Jupiter, contain resources that dwarf anything we have ever found on Earth. And between those asteroids, between the Moon and Mars and beyond, lies a frontier more vast than anything Columbus ever sailed toward. The gold rush that is coming will not be fought with pickaxes. It will not be won with covered wagons or dog-sled teams. It will be fought with rockets and robots and artificial intelligence and billions of dollars in investment capital. But it is the same story at its heart. Human beings staring at a distant horizon and deciding to go. Let us slow down for a moment and really sit with the numbers. Because one of the strangest things about space mining is that the scale of what is out there is so enormous that it almost stops making sense. Our brains are not designed to process it. We are going to try anyway. There are, according to current estimates, somewhere between 1 and 2 million asteroids in our solar system, larger than about 3/10 of a mile across. The total number of asteroids of all sizes is in the billions. Now, not all of these are rich in valuable minerals. Some are primarily made of silicate rock, the kind of stuff that makes up most of Earth's crust, useful but not extraordinarily valuable. But a significant fraction, particularly a class of asteroids known as M-type or metallic asteroids, are composed almost entirely of iron and nickel, with significant concentrations of precious metals like gold, platinum, palladium, and others. Let us talk about one specific asteroid to make this real. Its name is 16 Psyche. It sits in the asteroid belt between Mars and Jupiter. It is roughly 140 miles across. Scientists studying it believe that it is the exposed iron-nickel core of a protoplanet, essentially a dead world that had its outer layers stripped away by collisions billions of years ago. What is left is the core, pure metal. And the estimated value of the materials locked inside 16 Psyche? Early estimates placed it somewhere in the range of $10 quintillion. That is a 10 followed by 18 zeros. For reference, the entire global economy, every transaction, every dollar, every euro, every yuan exchanged on Earth in an entire year amounts to roughly $100 trillion. That is a 1 followed by 14 zeros. The wealth potentially locked inside 16 Psyche alone is roughly 100,000 times the size of the entire global economy. Now, those numbers come with enormous caveats, which we will get into. You cannot just scoop up all that metal and sell it, because doing so would instantly destroy the markets for those materials. The economics of space mining are far more complicated than they might first appear. But the point stands. The raw abundance of resources in the solar system is, by any measure we have, effectively unlimited compared to what exists on Earth. And that is before we even begin talking about the Moon, which has billions of tons of a material called helium-3 that could one day fuel nuclear fusion reactors, or the fact that water ice, which can be split into hydrogen and oxygen, effectively making rocket fuel, has been found at the lunar poles and in certain asteroids. Water is fuel in space, and fuel is power, and power in space is everything. Mars has vast mineral deposits of its own, although reaching and mining them at scale is a challenge for a further chapter in this story. Jupiter and Saturn's moons have oceans of liquid hydrocarbons and other exotic materials. The outer solar system is a treasure house that we have barely begun to catalogue. The resources are there, staggeringly, almost absurdly there. The real question is, how do we get them? And that is where the story gets truly interesting. Here is where the dreaming has to meet the engineering. Because knowing that there is an asteroid worth $10 quintillion floating in space is a bit like knowing that there is a diamond sitting on the bottom of the Mariana Trench. Knowing about it and actually getting it are two very different things. Let us walk through what space mining would actually look like, from beginning to end, in the most realistic version we can paint today. The first step is finding your target. This is actually further along than most people realize. Scientists have been cataloging and studying near-Earth asteroids, those that pass relatively close to our planet's orbit, for decades. There are now thousands of near-Earth asteroids catalogued in detail. We know their size, their composition, their orbital paths. We can calculate with remarkable precision exactly where they will be years and even decades from now. So the prospecting, in a sense, has already begun. It is being done with telescopes and radar dishes and spacecraft right now as you listen to this. The next step is reaching your target. Here is where rocket science literally becomes essential. Getting to an asteroid is not like flying an airplane to another city. You cannot just point a rocket at a rock and fly there in a straight line. Space travel works with orbital mechanics, the delicate, almost balletic art of using gravity and momentum to arc through space. A spacecraft heading to an asteroid might travel hundreds of millions of miles, taking months or even years to arrive, even though the asteroid itself might be, in cosmic terms, relatively close. The good news is that some near-Earth asteroids require only modest amounts of energy to reach, in some cases less energy than landing on the Moon, because the Moon's gravity makes landing and taking off expensive in terms of fuel. Once you reach an asteroid, the mining itself presents a fascinating set of challenges. On Earth, mining involves drilling, blasting, excavating, and transporting material. All of this depends on something we take completely for granted: gravity. Gravity is what keeps mining equipment anchored to the ground. It is what makes material fall when you blast it loose. It is what makes ore flow through pipes and channels. Asteroids have almost no gravity. A person standing on the surface of a large asteroid might weigh only a fraction of an ounce. Mining equipment set down on an asteroid's surface would need to be anchored somehow, or it would simply float away when it tried to dig. Several approaches have been proposed to solve this. One is to use harpoon-like anchoring systems that fire into the rock to hold equipment in place. Another is to wrap the asteroid in a kind of giant net or bag, which also serves the dual purpose of catching any material that is blasted loose. Some engineers have proposed spinning the asteroid to create artificial gravity, a concept that sounds far-fetched but is physically plausible with the right equipment. Others have suggested landing massive weights on the asteroid to create enough gravitational attraction. Once the mining is underway, the extracted material needs to be processed. Raw ore does not fly back to Earth. It needs to be refined, at least partially, before it can be used. Some proposals involve processing facilities in space, essentially small factories orbiting the asteroid or on its surface that separate the valuable metals from the worthless rock before shipping only the concentrated materials. And then there is the question of transportation. Getting mined materials back to Earth or to somewhere useful requires more orbital maneuvering. Heavy materials are expensive to move in space. One creative solution that has been seriously proposed is to not bring the materials back to Earth at all, at least not immediately. Instead, mined materials could be used in space itself to build structures, fuel spacecraft, or support human settlements on the Moon or Mars. In this vision, the solar system's resources are mined not to enrich people on Earth, but to bootstrap humanity's expansion into the cosmos. It is a lot to take in, but every single one of these challenges is being worked on right now by engineers and scientists at universities, national space agencies, and private companies around the world. This is not idle speculation, this is active engineering. Before humanity gets to the asteroid belt, there is a closer neighbor to consider. One that is only about 239,000 miles away, one that has been staring at us from the sky for the entirety of human history: the Moon. When people think about the Moon, they tend to think about the Apollo missions, those extraordinary, almost mythological moments in the late 1960s and early 1970s when 12 human beings walked on another world and came back with bags of rocks. At the time, those rocks were studied intensely, and the conclusion was somewhat anticlimactic. The Moon is geologically boring. Its surface is covered in a fine grey dust called regolith, and while that regolith contains oxygen, silicon, aluminum, iron, calcium and magnesium, all useful elements, it did not look like a treasure chest. But science, as it often does, has revised that picture over the decades. And what we now know about the Moon is considerably more exciting. First, water. The poles of the Moon, particularly the South Pole, are home to permanently shadowed craters, regions that have not seen sunlight in billions of years. Inside those craters, temperatures drop to nearly -400 degrees Fahrenheit, cold enough to trap water ice for billions of years. And there, in that permanent darkness, water ice has indeed been found, confirmed. It is there, not in tiny amounts either. We are talking about hundreds of millions of tons of water ice, potentially billions of tons, locked in the South Polar region alone. Water, as we touched on earlier, is not just water in space. Water is oxygen for astronauts to breathe. Water is hydrogen for rocket fuel. Water is the foundation of life support systems. Water is the resource that makes sustained human presence on the Moon not just possible but practical. Before the discovery of lunar water ice, the idea of permanently based humans on the Moon required hauling every drop of water from Earth, an extraordinarily expensive proposition. With lunar ice, a Moon base could, in theory, sustain itself. Beyond water, the Moon has something else that has scientists genuinely excited: helium-3. This is a lighter isotope of helium, meaning a version of helium with a slightly different atomic structure, and it is extraordinarily rare on Earth. Earth's magnetic field and atmosphere deflect most of the helium-3 that comes streaming in from the Sun, so virtually none of it reaches our surface. The Moon has no such protection. For billions of years, the solar wind has been blasting helium-3 into the lunar regolith, and it has been accumulating there ever since. Why does this matter? Because helium-3 is considered one of the most promising fuels for a future technology, nuclear fusion. Fusion, the same process that powers the Sun, has been the holy grail of energy research for decades. A fusion reactor that burns helium-3 produces enormous amounts of energy with very little radioactive waste compared to conventional nuclear fission. Scientists estimate that a single space shuttle payload bay filled with helium-3, roughly 55 pounds of material, could power the entire United States for a year. The Moon may have somewhere in the range of 1 million tons of helium-3 in its regolith. The potential energy value of that is, again, a number that barely fits into comprehension. Now, it is important to be honest, nuclear fusion that can actually use helium-3 at commercial scale does not yet exist, but it is being actively developed. Companies and government programs around the world are racing to make fusion power a reality, and many of them have helium-3 on their roadmap as the fuel of choice. The Moon's helium-3 is a resource waiting for the technology to catch up with it. There is also the matter of rare earth elements. Despite their name, rare earth elements are not actually that rare on Earth. They are just geographically concentrated in ways that create political and supply chain headaches. China controls the vast majority of the world's rare earth production. These elements, neodymium, europium, terbium, and others, are absolutely critical for electronics, wind turbines, electric vehicle motors, and military technology. The Moon's regolith contains these elements as well, and in a world where access to rare earths is increasingly a geopolitical flashpoint, a lunar source that no single country controls becomes a very interesting proposition. All of this explains why, after more than 50 years of relative quiet, the Moon has become the focus of an intense new wave of attention. The United States, China, India, Japan, the European Space Agency, Russia, and a growing list of private companies are all either on the moon, planning missions to the moon, or developing the technology to establish a permanent presence there. The moon is not a dead end of the space age. It is the beginning. If you are finding this journey through the cosmos as fascinating as I am, go ahead and hit that like button. And if you haven't yet, subscribe so you do not miss the second half of this story. Your support genuinely means a great deal, and it helps this channel keep making content like this. Here is where the story shifts from the abstract to the deeply human. Because behind every rocket, every asteroid survey, every lunar landing proposal, there are people. Entrepreneurs, scientists, engineers, dreamers who looked at the conventional wisdom that space is only for governments and decided that the conventional wisdom was wrong. The private space revolution has a name that most people know: SpaceX. Founded by Elon Musk in 2002, with the stated goal of making humanity a multi-planetary species, SpaceX has done something that most aerospace experts genuinely thought was impossible. It dramatically reduced the cost of getting to orbit. The Falcon 9 rocket, with its reusable first stage that lands itself on drone ships in the middle of the ocean, has cut launch costs by an extraordinary margin. And that matters enormously for space mining, because the single biggest cost in any space venture is getting off the ground. But SpaceX, for all its fame, is not the company most directly pursuing space mining. For that, we need to look at a different cast of characters. Planetary Resources was founded in 2012 by a group of visionaries that included the entrepreneur Peter Diamandis and the filmmaker and deep-sea explorer James Cameron, among others. The company's explicit goal was to mine near-Earth asteroids. It attracted serious investment and serious scientific talent. It launched demonstration satellites, it mapped potential target asteroids, and then in 2018, it ran out of money and was acquired by a blockchain company and effectively ceased operations. It was a cautionary tale about how difficult it is to turn a grand vision into a sustainable business, especially when the timeframes involved are measured in decades, not quarters. Deep Space Industries was another early pioneer, founded around the same time with similar goals. It developed prospecting technologies, proposed novel mining concepts, and then was acquired by Bradford Space in 2019 and pivoted away from its mining ambitions. These early failures are not the end of the story. They are, if anything, a familiar chapter in the history of any transformative industry. The first wave of aviation companies mostly went bankrupt. The first wave of internet companies mostly went bankrupt. The pioneers clear the ground, prove what is possible, and then a second wave, better funded, better informed, and building on the lessons of the first, comes in and actually makes it work. That second wave is now building. Astroforge, a California-based company founded in 2022, has taken a different and arguably more pragmatic approach. Rather than trying to do everything at once, prospect, travel, mine, process, return, they are focused specifically on the refining side of the equation. Their plan is to launch processing hardware into space to refine asteroid material in orbit, and they have already launched a demonstration mission to test their technology. They are small, scrappy, and intensely focused, the kind of company that could either flame out or become legendary, and it is too early to tell which. Transastra is working on what they call optical mining, using concentrated sunlight to heat up an asteroid and essentially cook out the volatile materials, like water and carbon dioxide, which can then be collected and used as fuel. It is an elegant concept that sidesteps the mechanical difficulties of actually drilling into an asteroid's surface. Carmen Plus is looking at lunar regolith extraction, focused on the practical near-term goal of extracting oxygen from the moon's surface for life support. And then there is iSpace, a Japanese company that became famous and heartbreaking when its Resilience lander crashed on the moon in 2023, becoming the first privately funded company to reach the lunar surface, even if not quite in the intended fashion. They launched a second mission. They are still in the game. The cast of characters is international. Chinese companies backed by a government that has made space a national priority are developing their own capabilities at a rapid pace. European startups are emerging. Indian space ambitions, supercharged by the success of India's Chandrayaan-3 mission, the first spacecraft to land near the lunar South Pole, are growing by the year. This is not a story with one hero, it is a story with dozens, hundreds. A whole civilization beginning to look up. Here is where things get philosophically thorny. And in a story full of extraordinary ideas, this might be the most extraordinary of all, because it touches something fundamental about how human civilization organizes itself. Who owns the resources in space? The Outer Space Treaty of 1967 is the foundational document of international space law. Written at the height of the space race, it was signed by the United States, the Soviet Union, the United Kingdom, and eventually over 100 other nations. Its core principle is elegant and idealistic. Space is the province of all mankind. No country can claim sovereignty over the moon, an asteroid, or any other celestial body. The moon in this framework belongs to everyone, which effectively means it belongs to no one in a legal sense. The Outer Space Treaty was designed for a world where only governments went to space, and where the primary concern was preventing one superpower from militarizing the moon or planting a flag on Mars and claiming it as territory. It was not designed for a world in which private companies want to land a robot on an asteroid and pull out platinum to sell. And so we have a legal ambiguity of historic proportions. Does the Outer Space Treaty prevent a company from mining an asteroid? Technically, it prevents nations from claiming the asteroid itself. But does it prevent a company or a person from extracting and owning the resources that come out of that asteroid? Is there a difference between owning the land and owning what you dig up from it? The United States took a clear position in 2015 when Congress passed the Commercial Space Launch Competitiveness Act. That law states explicitly that any US citizen who extracts a resource from a celestial body has the right to own, use, and sell that resource. It does not claim the asteroid itself, but it asserts property rights over what comes out of it. Several other countries have passed similar laws since then: Luxembourg, the UAE, Japan. Luxembourg, interestingly, has become something of a hub for space mining companies precisely because of its favorable legal framework, a small European nation positioning itself as the jurisdiction of choice for an interplanetary industry. Not everyone accepts this interpretation. Russia and other nations have argued that allowing private companies to own space resources violates the spirit of the Outer Space Treaty's principle that space is the common heritage of mankind. This is not just abstract legal argument. It has real implications for whether international cooperation in space remains possible, or whether space becomes another arena for geopolitical competition and conflict. The Artemis Accords, promoted by the United States and signed by a growing number of nations, attempt to establish a framework for how space resources can be used and how conflicts can be avoided. They encourage transparency, prohibit harmful interference between missions, and establish the concept of safety zones around lunar operations. But they are not binding international law. They are more like a set of best practices that the signing countries agree to follow. China and Russia have notably not signed the Artemis Accords. They have their own framework, the International Lunar Research Station project, which they are developing with a different set of partner nations. The moon, in a very real sense, is already becoming geopolitically contested. This legal complexity matters for space mining in a deeply practical way. Companies need legal certainty before they invest billions of dollars in a venture. You cannot spend a decade building a spacecraft and a decade more developing a mine if you're not sure whether you will actually own what you extract. The legal frameworks being built right now, imperfect, contested, but being built, are as important to the future of space mining as any rocket engine or drilling robot. What happens when two countries both claim the rights to the same resource deposit? What happens when a privately mined asteroid's resources flood the global market and crash commodity prices on Earth? What happens if a mining operation causes some kind of catastrophic damage, say deflecting an asteroid in a way that accidentally changes its orbit? None of these questions have clear answers yet. They are questions that civilization will have to answer, probably under significant pressure, in the coming decades. The legal frontier of space is, in some ways, wilder than the physical one. Let us step back from the stars for a moment and think about money. Because the economics of space mining are genuinely counterintuitive, and understanding them changes how you think about the whole enterprise. Here is the basic puzzle. If you brought back a huge amount of platinum from an asteroid, would it actually be worth anything? The price of platinum, like the price of gold, silver, cobalt, or any other mineral, is determined by supply and demand. Right now, platinum is valuable partly because it is rare. It is hard to find, expensive to mine, available only from a handful of countries, primarily South Africa and Russia. The global production of platinum is roughly 5 to 6 million troy ounces per year. The price is, at various times, somewhere between $1,000 and $2,000 per ounce, making it a multi-billion-dollar market annually. Now imagine that a space mining company arrives with a spacecraft full of platinum. Not 5 million ounces, not 50 million ounces, millions of tons. The price of platinum would collapse instantly. The company that spent billions building the mine would find that its product was now nearly worthless. This is not a hypothetical. It is a real economic puzzle that every serious space mining company has to grapple with. The answer, most economists and industry analysts believe, is not to flood the market. It is to bring resources back gradually in amounts calibrated to what the market can absorb. Or, and this is the more exciting answer, to use those resources in space rather than on Earth, where the economics work completely differently. In space, water is worth more than gold. That is not hyperbole, it is arithmetic. Right now, it costs roughly tens of thousands of dollars per pound to launch anything from Earth's surface into orbit. Water, for drinking and for use as rocket propellant, is absolutely essential for sustained human presence beyond Earth. If you can mine water ice from the Moon or a nearby asteroid and sell it to spacecraft in orbit, you are selling into a market where the competition, water launched from Earth, is extraordinarily expensive. You do not need to crash commodity prices on Earth. You just need to supply a space economy that is going to need those resources in any case. This is the vision that underlies most of the most credible business plans in space mining today. The goal is not to replace Earth's mining industry. The goal is to supply a growing space economy, space stations, moon bases, Mars missions, with the materials they need without the crushing expense of lifting everything from Earth's surface. And then there is a longer-term vision that is even more radical. If space mining can supply the solar system with resources in abundance, the pressure on Earth's environment would dramatically decrease. Right now, mining on Earth is one of the most destructive industries the planet faces. Rainforests are cleared, rivers are polluted, indigenous communities are displaced. The demand for minerals like cobalt, essential for electric vehicle batteries, has fueled conflict and exploitation in places like the Democratic Republic of Congo. If even a fraction of that demand could be met by resources extracted in space, the relief to Earth's ecosystems and to the communities most harmed by mining would be extraordinary. Some thinkers take this idea to an almost utopian extreme. They envision a future where all heavy industry, all the dirty, resource-intensive, polluting work of manufacturing is moved off Earth entirely. Earth becomes a garden world, protected and restored, while humanity's industrial activity happens in space, where there is no environment to damage, where resources are effectively unlimited, and where the waste products of industry simply drift away into the void. It is a beautiful idea. It is also at least a century away. But the fact that it is even imaginable that it exists as a logical endpoint of the technologies we are developing today, says something profound about the stakes of what is being built right now. We have talked about gold and platinum. We have talked about water and helium-3. But there is another category of space riches that captures the imagination in a different way. And that is the world of carbon-based space materials, including, yes, actual diamonds. Let us start with a spectacular finding from the world of planetary science. Uranus and Neptune, the two outermost ice giant planets in our solar system, are believed to have interiors where the pressure is so extreme that carbon atoms are literally compressed into diamonds. These diamonds, large, potentially massive, raining down through the high-pressure interior of a planet like precious stones falling in a storm, are real. Scientists have replicated the conditions in laboratory experiments, confirming that at the pressures found in the interiors of those planets, diamond rain is not just possible but likely. Uranus and Neptune may have oceans of liquid diamond, with solid diamond icebergs floating in them. We are not going to mine Uranus anytime soon. It is about 1.6 billion miles away at its closest approach to Earth, and we have sent exactly one spacecraft past it, Voyager 2, in 1986. But the existence of those diamonds is a reminder that the universe is not stingy with its riches. The elements that make diamonds, carbon, are among the most common in the cosmos. The conditions that create them exist across the solar system and beyond. Closer to home, certain classes of meteorites, rocky fragments that have fallen to Earth from space, contain tiny diamonds. These nanodiamonds, as they are called, are believed to form in the outer layers of dying stars and were incorporated into our solar system when it formed from a collapsing cloud of gas and dust. They are extraordinary, ancient star stuff embedded in rocks that fall from the sky. And they are not the only exotic carbon material found in meteorites. There is also a carbon molecule called Buckminster fullerene, or buckyball, a cage of 60 carbon atoms arranged like the panels of a soccer ball that has been found in meteorites. Buckyballs have remarkable properties. They can trap atoms inside them. They can be extremely strong, and they have potential applications in medicine, materials science, and electronics. They are named after the architect and futurist Buckminster Fuller, and their discovery earned a Nobel Prize in chemistry. The fact that they exist in meteorites means they form naturally in space, and the right kind of asteroids might contain them in abundance. But let us bring the diamond story a bit closer to Earth. The asteroids known as carbonaceous chondrites, a very common class of asteroid, contain carbon compounds in enormous quantities, along with water, organic molecules, and other materials that are extraordinarily interesting to both scientists and engineers. The Hayabusa 2 mission, a Japanese spacecraft, traveled to an asteroid called Ryugu in 2018 and brought back a sample. When scientists analyzed what came back, they found water and organic molecules, the building blocks of chemistry that on Earth is associated with life. These are not signs of life on the asteroid, but they are a reminder that the chemistry of the universe is rich and complex, and that the resources we might find in space are not limited to the metals we think of as valuable in purely financial terms. Carbon materials in space also have a profound relevance to a technology that is reshaping our world: carbon fiber. Carbon fiber, incredibly strong, incredibly light, is used in aircraft, spacecraft, sports equipment, and increasingly in automobiles. Manufacturing it on Earth requires significant energy. Some researchers have speculated that carbon-rich asteroids could be a future source of the raw material for carbon fiber and related composite materials, potentially manufactured in space for use in space structures. The diversity of valuable materials out there goes far beyond what you could list in a single evening. Every class of asteroid has its own profile of riches. Every moon in the solar system has its own character. The more we learn, the richer the catalogue of what is waiting to be found. We have talked about economics, about legal frameworks, about science. But there is something we have not yet addressed, and it is perhaps the most important factor of all, the human one. Because at some point, maybe not in our lifetimes, maybe in the lifetimes of children being born right now, human beings are going to go to these places. Not just robots, not just automated systems, people. And what would that actually feel like? Imagine for a moment that you are one of the first asteroid miners. Your spacecraft, after a journey of several months, has matched velocities with your target, a half-mile wide metallic asteroid officially designated 2002 AT4, but which your crew has taken to calling the Anvil because of its blunt, ungainly shape. You suit up in a pressurized suit and float out of the airlock. The asteroid hangs before you, filling half your field of vision. It is not the dramatic, craggy rock of science fiction movies. Up close, it looks almost gentle. A slow, tumbling mass of dark metal, its surface pocked with ancient impact craters, dusted with a fine layer of material accumulated over billions of years. The sun is visible but smaller than it appears from Earth. Still dazzling, still the king of the solar system, but somehow more distant, more indifferent. The stars are everywhere. Without an atmosphere to scatter light, they are breathtaking, thick and bright, and absolutely still, a canvas of light stretched in every direction. The asteroid is rotating slowly. Slowly enough that you can work on its surface without feeling dizzy, but you have to be careful. If you push off the surface too hard, there is almost no gravity to pull you back. You could drift away. Your suit has small thrusters for exactly this reason, tiny puffs of cold gas that allow you to maneuver in microgravity. It is not walking, it is not flying. It is something in between, something that has no word in any earthly language because nothing on Earth is quite like it. Attached to the Anvil's surface, anchored with drills that bit into the rock months ago during the automated setup phase, is the mining platform. It is not large, maybe the size of a shipping container, bulky with equipment, its surface covered in solar panels and thermal radiators. From it extend articulated arms bearing cutting heads and collection bags. The platform is already working, has been working for weeks, cutting into the asteroid's surface and collecting material. The collected ore, already partially processed by the automated systems, floats in sealed bags nearby, tethered to the platform. Your job today is maintenance, checking the anchors, replacing a worn cutting head, verifying the integrity of a seal on one of the collection bags. It is, in a sense, unglamorous work, plumbing and metalwork and quality checks. Except that you are floating next to a billion-year-old metal world with the entire solar system arrayed around you and the silence of the void pressed close against the outside of your helmet. This is how it will begin, not with drama and conquest, with patience and maintenance and slow, careful work in an environment where a small mistake can become a catastrophic one. The pioneers of space mining will be, above all else, people who are calm under pressure, who can do precise work in an environment that tries to kill them with cold and vacuum and radiation, who can stay focused on the job when the view from their office window is, quite literally, infinity. Over time, the work will become routine. The way deep-sea oil drilling became routine. The way any frontier work eventually becomes routine once the infrastructure is in place and the techniques are understood. But the first generation of people to do it will never quite shake the awareness of where they are, of what they are part of. They will be the gold rush miners of the space age, and history will remember them the way we remember the prospectors of 1848 and the whalers of Nantucket and the navigators who crossed the Pacific with nothing but stars to guide them, as the people who went first, who made the impossible ordinary, who pushed the edge of what human beings are willing to attempt, and found, as people always have, that the edge was farther out than anyone imagined. We are halfway through this story, and the greatest chapters are still to come. If you are enjoying this journey through the cosmos, please take a moment to like this video and subscribe to the channel. It truly helps more than you might think. and it means that more people get to hear stories like this one. Thank you, truly. In the last chapter, we imagined what it would feel like to be a human miner floating beside a metallic asteroid. And while that image is real, people will eventually go to these places. The truth is that for the first many decades of space mining, the workers will not be human at all. They will be machines, robots, autonomous systems guided by artificial intelligence, operating in environments so hostile and so remote that sending a human being there would be, for a very long time, impractical. This is actually good news. Because robotic technology has been advancing at a breathtaking pace, and the capabilities that are now available or nearly available are extraordinary enough to make the early stages of space mining genuinely feasible in ways that were not true even 15 years ago. Let us start with the most fundamental challenge: operating autonomously at enormous distances. When a spacecraft is at an asteroid in the inner solar system, a radio signal traveling at the speed of light can take anywhere from a few minutes to over 20 minutes to reach it, depending on where Earth and the asteroid are in their respective orbits. This means you cannot remotely control a robot the way you might control a drone in your backyard. You send a command and you wait. You might send a command and not know if it worked for 40 minutes. In that time, the robot has to be able to make decisions on its own, handle unexpected situations, and keep operating safely without any input from Earth. This requirement, autonomous operation under uncertainty, in an environment you cannot fully predict in advance, is exactly the challenge that modern artificial intelligence is being developed to solve. The same machine learning systems that allow a self-driving car to navigate a busy city street are being adapted in specialized forms for space robotics. The idea is to give robots the ability to perceive their environment, reason about it, and act on it without waiting for a human to tell them what to do. NASA's Perseverance rover on Mars, still rolling across the red planet as you listen to this, is an early example of what this looks like in practice. Perseverance is not fully autonomous in the way future mining robots will need to be, but it has significantly more onboard intelligence than any previous Mars rover. It can navigate around obstacles, select its own science targets, and perform certain operations entirely on its own. Each generation of space robot is smarter than the last, and the rate of improvement is accelerating. For space mining specifically, the robotic systems being designed have to do things that no robot has ever done before. They have to anchor themselves to a surface with almost no gravity. They have to cut through rock or through pure metal, depending on the asteroid type, in a vacuum environment where the thermal properties of the material behave very differently than they do on Earth, because there is no air to carry heat away. They have to handle fine-grained material without creating clouds of floating debris that could damage other equipment. They have to process ore, separate valuable from worthless material, package the results, and maintain themselves over years of continuous operation in an environment bathed in radiation that gradually degrades electronics. It is a formidable set of requirements. But consider what the mining industry has already accomplished on Earth with robotics. Modern large-scale mines, particularly in Australia and Canada, are already almost entirely automated. Giant autonomous trucks, each one the size of a small house, move millions of tons of material without a human driver. Drilling rigs operate on their own. Processing facilities run 24 hours a day with minimal human supervision. The mine of the future, in the minds of the people building it, is already beginning to look more like a data center than the mines of the 19th century. Quiet, ordered, full of sensors and software rather than sweat and muscle. Translating that competence into space requires solving new problems, but it builds on a foundation of automated mining technology that is already mature. The path forward is challenging, but clear. There is also a technology that is beginning to play a major role in space exploration, that will be equally critical for space mining: three-dimensional printing or additive manufacturing. The idea of manufacturing things in space rather than building everything on Earth and launching it is a game-changer for economics. Launching material from Earth's surface is crushingly expensive. But if you can mine raw material on the Moon or an asteroid and use it to 3D print the components you need in situ, right there, on site, you begin to break the tyranny of Earth's gravity well. NASA and various private companies have already demonstrated that 3D printing works in microgravity. Items have been printed on the International Space Station. Designs are being developed for printers that can work with lunar regolith, the Moon's surface dust, as their raw material, essentially printing structural components directly from moon rock. It is early, it is imperfect, but it is real. The technology picture for space mining, when you survey it honestly, is one of genuine progress on multiple fronts simultaneously. Robotics, artificial intelligence, launch cost reduction, additive manufacturing, materials science, all of these are advancing in ways that converge on the same destination: an industry operating beyond Earth that does not need to rely on Earth for everything. Not everything about the future of space mining is driven by profit and engineering ambition. Some of it is driven by the same force that has shaped human history for as long as there have been nation-states' power. The desire of nations to control resources, secure advantages, and ensure that their rivals do not get there first. The space race of the 1960s was famously not primarily about science. It was about geopolitical prestige and military capability. The rockets that launched American astronauts to the Moon were direct descendants of the missiles designed to carry nuclear warheads across continents. Space was always, at its heart, an extension of the competition between great powers, a competition that never really went away, even after the flags were planted and the Apollo program was wound down. That competition is back. And this time, it has an economic dimension that the original space race never had, because the resources at stake are not symbolic, they are real. China has been extraordinarily clear about its intentions in space. The Chinese National Space Administration has set out a roadmap that includes crewed lunar missions, a permanent moon base, what they call the International Lunar Research Station, and the development of space-based solar power, which would require mining significant quantities of material in space or on the Moon. China has launched multiple robotic lunar missions in the past decade, and its Chang'e 6 mission brought back samples from the Moon's far side. The first time any spacecraft has ever done that. China is not exploring as a hobby. It is building infrastructure and capability with deliberate, long-term strategic intent. The United States, for its part, has responded with the Artemis program, its plan to return American astronauts to the Moon for the first time since 1972. The Artemis program is not just about planting flags, it is about establishing a sustained human presence at the lunar South Pole, precisely where the water ice is concentrated. The choice of landing site is not accidental. Whoever establishes a functioning presence at the South Pole first will have a significant practical advantage in accessing the most valuable resource on the Moon. NASA's stated goal is to have a crewed landing on the Moon within this decade, followed by the Lunar Gateway, a small space station in lunar orbit that will serve as a staging point for surface operations. India, after the historic success of Chandrayaan-3 landing near the South Pole in 2023, has signaled its own ambitious plans for lunar resource utilization. Japan, through its JAXA space agency and a growing private sector, is deeply engaged in lunar and asteroid exploration. The European Space Agency has proposed a concept called Moon Village, an international multi-use lunar presence that would include resource extraction among other activities. The potential for conflict is real. Imagine two nations or two companies both targeting the same water ice deposit at the lunar South Pole. The deposits are not infinite. The best sites with the highest concentrations of ice in easily accessible locations are limited. A site staked out and occupied by one party becomes unavailable to others, not because any law says so, but simply because it is occupied. First mover advantage in space, as in so many industries, may be decisive. The Artemis Accords, as mentioned in previous chapters, attempt to manage these tensions by establishing norms of behavior, safety zones, transparency requirements, interoperability standards. But they are not binding international law, and their effectiveness depends entirely on whether the parties involved choose to honor them. China and Russia, not signatories, are under no obligation to follow them. There is a scenario, not implausible, in which the competition for space resources becomes a source of serious international tension over the coming decades, in which the legal ambiguities we discussed earlier are tested not in courts, but in the far more difficult arena of geopolitical confrontation, in which the next great resource race, like the scramble for Africa in the 19th century, or the competition for oil in the 20th, is played out not on Earth but above it. There is also a more hopeful scenario, in which the sheer difficulty and expense of space operations drives nations and companies to cooperate rather than compete, simply because the problems are too large for any one actor to solve alone. The history of the Antarctic, a continent governed by an international treaty that has kept it peaceful and scientifically productive for decades, suggests that international cooperation in extreme environments is possible when the incentives are right. Which of these futures materializes will depend on choices that are being made right now in government ministries and corporate boardrooms and diplomatic negotiations. It is one of the most consequential stories unfolding in the world today, even if it rarely makes the front page. Let us go further, past the moon, past the asteroid belt, and out to the place that has captured human imagination perhaps more than any other, the red planet, Mars. Mars is not often thought of in the context of mining. When people imagine Mars, they tend to imagine dust storms and frozen deserts, and the tantalizing, still unresolved question of whether life ever existed there. But Mars is also, from a resource standpoint, an extraordinarily interesting world, and understanding it is essential for understanding the long-term future of human civilization beyond Earth. Let us start with the basics. Mars is about half the diameter of Earth, with roughly a third of Earth's gravity. Its atmosphere is thin, about 1% the density of Earth's, and composed primarily of carbon dioxide, with traces of nitrogen and argon. The surface temperature averages about -80 degrees Fahrenheit, though it varies enormously by location and season. There is no liquid water on the surface today, but the evidence for water in Mars's past is overwhelming. Vast river valleys, ancient lake beds, minerals that only form in the presence of water, all of these tell the story of a warmer, wetter Mars billions of years ago. And there is water on Mars today, locked in the polar ice caps in enormous quantities. The North Polar Ice Cap of Mars contains enough water ice that, if melted, it would cover the entire planet to a depth of roughly 36 feet. There is also evidence for significant permafrost, frozen water mixed with soil at mid-latitudes. Water, again, is the critical resource. Water on Mars would support human life, provide oxygen, and split into hydrogen and oxygen, provide fuel for spacecraft. Beyond water, Mars has extensive mineral deposits of iron oxide, the rusty red iron mineral that gives the planet its color. Iron and oxygen, both extractable from the Martian surface, are the raw materials for steel. The idea of manufacturing steel on Mars, using Martian resources rather than materials brought from Earth, is central to virtually every serious plan for long-term human habitation there. It is not enough to land people on Mars. You have to build things for them to live in, work in, travel between. And if all of those structures have to be shipped from Earth, the economics never work. The only viable Mars colony is one that becomes increasingly self-sufficient, and mining is the foundation of that self-sufficiency. Mars also has significant deposits of sulfur, silicon, and various other minerals useful for construction and manufacturing. Some researchers have even identified potential deposits of carbonates and sulfates that could be useful for chemical processing. Mars is not a treasure planet in the way that metallic asteroids are. It is not going to yield gold or platinum in extraordinary quantities. But it is a world rich enough in practical, structural materials to potentially support a self-sustaining civilization. There is also the question of Mars's moons. Phobos and Deimos are two tiny, irregularly shaped moons that orbit very close to Mars. Both are believed to be captured asteroids, and Phobos in particular, only about 17 miles across, orbits so close to Mars that it completes an orbit every 7.5 hours. Phobos may be rich in carbonaceous material and possibly water ice. More interestingly, it sits in a low-gravity environment between Mars and space, making it potentially useful as a staging point, a place where materials mined from Mars could be processed and stored before being used or shipped onward. The timeline for Mars mining is longer than for the Moon or near-Earth asteroids. Getting to Mars takes between 6 and 9 months with current technology, and the journey requires careful timing. Mars and Earth are only in favorable alignment for launches every 26 months. A round trip is a commitment of at least 2 years, and the communication delays between Mars and Earth at their farthest apart can reach 24 minutes one way. An industrial operation on Mars is a generational project, not a decade-long one. But the vision is compelling. A Mars that is home to human beings mining its own resources, building its own infrastructure, growing in population and capability. This is not merely a mining story, it is a civilization story. The first step toward humanity becoming a genuinely multiplanetary species is establishing that it is possible to live off the land somewhere other than Earth. Mars is where that question will be tested. Pause for a moment. Take a breath. Because in our enthusiasm for all of this, the gold, the platinum, the water, the diamonds in the sky, it is worth asking a question that does not always get asked in conversations about space mining. A harder question. A more uncomfortable one. Is it right? Now, this might seem like a strange thing to ask about rocks floating in space. Nobody lives on an asteroid. No civilization has staked a claim to Psyche 16. There are no ecosystems to damage in the asteroid belt, no communities to displace, no rivers to pollute. By any conventional definition of environmental ethics, mining an asteroid would seem to be about as morally neutral as picking up a pebble from a parking lot. But some philosophers and scientists argue that the ethics of space mining are not quite that simple, and their arguments, even if you ultimately disagree with them, are worth understanding. The first argument concerns Mars, and it is actually a very serious one. Mars, unlike the asteroid belt, might not be lifeless. The evidence for past life on Mars is circumstantial, but accumulating. More intriguingly, some scientists believe that microbial life could still exist on Mars today, perhaps in subsurface pockets of liquid water kept warm by geothermal activity, sheltered from the harsh surface radiation. We do not know. We have not yet conclusively proven either the presence or absence of life on Mars. If life exists on Mars, even simple, microscopic life, then the question of whether we have the right to industrialize that planet becomes very different. Single-celled organisms are not endangered whales or ancient forests, but they would represent an independent origin of life, life that arose separately from Earth life, a second data point in the universe's experiment with biology. The scientific value of that discovery would be incalculable. And the moral weight of potentially destroying it, even inadvertently through contamination, is something that serious thinkers have argued deserves careful consideration. NASA and other space agencies already take this seriously. It is called planetary protection, and it involves extensive procedures to sterilize spacecraft before they land on potentially habitable worlds, precisely to avoid contaminating those worlds with Earth microbes that might either harm native life or be mistaken for it. These protocols are not theatre. They reflect a genuine commitment to the principle that the scientific integrity of another world matters. But planetary protection is about science, not ethics, in a broader sense. The deeper ethical question is, even if Mars has no life, even if it is completely and irreversibly dead, do we have an obligation to preserve it in something like its natural state? Is there intrinsic value in a pristine Martian landscape that has been unchanged for 3 billion years? Most people, if they are honest, would probably say no. A dead Mars is just rocks, and humans have always used the resources around them. That is not a character flaw. It is how civilizations are built. But the conversation is worth having, because the decisions we make now about how to approach space resources will set precedents that govern how we behave for centuries. There is also a justice question, one that is very much rooted in earthly concerns. The Outer Space Treaty declares that space is the common heritage of mankind. But the companies and countries racing to get there first are, almost without exception, wealthy, technologically advanced, and located in the global north. If the resources of the solar system are developed primarily by American and Chinese and European and Japanese interests, and the wealth flows primarily to those economies, what does that mean for the rest of humanity? For the billions of people in countries that will never have a space program, that will never have a stake in the asteroid mining industry, that will receive only the trickle-down effects, if any, of the greatest resource rush in history, this is not a settled question. It is not even a widely discussed one, given that most of the people talking about space mining are the same people who stand to benefit from it most directly. But it is a real question, and one that any honest accounting of the space mining future has to grapple with. And then there is the philosophical dimension that is perhaps the strangest of all, the question of what we are doing to ourselves. Human civilization has always been shaped, in part, by the experience of scarcity, by the knowledge that resources are limited, by the discipline that constraint imposes. If the solar system's resources are effectively unlimited, if the long-term future is one of genuine material abundance, how does that change the human story? Does abundance liberate us, allowing us to finally address poverty and suffering on Earth without the zero-sum competition that has driven so much conflict? Or does it simply raise the stakes of competition, giving powerful actors even more reason to race and fight and claim? History does not give us clean answers. The abundance produced by the Industrial Revolution did not eliminate poverty or end war. The Green Revolution in agriculture did not solve hunger. Abundance tends to be captured and concentrated by those who are already in a position of power, rather than spreading evenly. Whether space resources will be different, whether some combination of technology, policy, and human choice can make the wealth of the solar system genuinely common, is the great open question of the next several centuries of human history. Here is a turn in the story that might surprise you. Because space mining is not only about extracting resources, it is also potentially one of the most important tools humanity has for protecting life on Earth. You may have heard of the asteroid that killed the dinosaurs. 66 million years ago, a rock roughly 6 miles across struck what is now the Yucatan Peninsula in Mexico. The impact released energy billions of times greater than any nuclear weapon ever detonated. It vaporized everything within hundreds of miles instantly. It sent a shockwave around the planet. It threw enough debris into the atmosphere to block the sun for months, collapsing food chains and driving roughly 3/4 of all species on Earth, including all non-avian dinosaurs, to extinction. That event is not ancient history in the cosmic sense. It was not a one-time thing. It is part of an ongoing process. There are, right now, thousands of near-Earth asteroids, rocks large enough to cause regional or global catastrophe, that have not yet been fully catalogued. Of those that have been catalogued, the vast majority pose no threat to Earth in the foreseeable future. But a small number are designated as potentially hazardous objects, meaning their orbits come close enough to Earth's that there is at least some possibility of a future impact. The probability is low for any given object. The consequences, if it happened, would be catastrophic. This is not science fiction. In 2013, a meteor about 65 feet across, tiny by asteroid standards, entered Earth's atmosphere over Chelyabinsk, Russia, and exploded in the air. The shockwave shattered windows across a wide area, injuring over 1,400 people. If it had been a little larger, or struck a populated area more directly, the death toll could have been enormous. And Chelyabinsk-sized objects are among the smallest that could cause significant damage. Objects a quarter-mile across could devastate a region the size of a large state. Objects a mile across or larger could have global effects. The good news is that we now have the ability, at least in principle, to deflect asteroids that are on collision courses with Earth. NASA's DART mission, launched in 2021 and impacting the small asteroid moon Dimorphos in 2022, demonstrated this conclusively. A spacecraft the size of a vending machine, traveling at about 14,000 miles per hour, struck Dimorphos and measurably changed its orbital period. It worked. Asteroid deflection is not theoretical anymore. We have done it, but deflection requires time. You have to know an asteroid is coming well in advance, ideally decades in advance, to have enough time to build and launch a deflection mission and have it make a meaningful difference. That means finding and tracking potentially hazardous asteroids is an urgent priority. And here is where space mining enters the picture in a surprising way. The same infrastructure that would support an asteroid mining industry. The telescopes, the spacecraft, the robotic systems, the detailed knowledge of asteroid compositions and orbital mechanics is also exactly the infrastructure you need to identify and respond to asteroid threats. A well-developed space mining industry would, essentially as a side effect, give humanity an early warning system and response capability for asteroid impacts that we currently lack. There is even a more direct connection. Mining an asteroid requires knowing its exact composition and internal structure, something we currently can only estimate from afar. Understanding an asteroid intimately, the way miners would, gives us much better models for how to deflect it if needed. And the equipment used to mine an asteroid, the robotic systems, the propulsion technologies, the ability to operate on and around an asteroid for extended periods is directly applicable to an emergency deflection mission. Space mining, in this light, is not just an economic venture, it is planetary defense. The investment that goes into developing the industry simultaneously builds the capability to protect Earth from one of the most catastrophic risks our species faces. There is something deeply satisfying about that double purpose. The treasure hunters and the defenders of civilization, it turns out, need much the same tools. We touched on this idea earlier, but it deserves its own chapter, because it is central to understanding how a genuine space economy, not just space mining, but a whole ecosystem of activity beyond Earth, would actually function. The idea is simple enough to state, and profound enough to sit with for a while. Water is the oil of space. On Earth, oil's power as an economic resource comes from two things. It is energy dense, and it is found in specific locations, making it possible to control and trade. Whoever controls the oil controls economies, armies, and political systems. The 20th century was, to a significant degree, the century of oil, and the geopolitics of oil, the Middle East, OPEC, the Gulf Wars, shaped the modern world. In space, water plays an analogous role. Here is why. Water, as a molecule, is composed of 2 hydrogen atoms and 1 oxygen atom. Hydrogen and oxygen, under the right conditions, combine to form the most energetic chemical propellant known, liquid hydrogen and liquid oxygen rocket fuel. This is what powered the engines of the Saturn V rocket that sent Apollo astronauts to the Moon. It is what powers many modern spacecraft. Hydrogen-oxygen propulsion is exceptionally efficient in rocketry terms. It has a very high specific impulse, meaning you get a lot of thrust for a given mass of fuel. If you can mine water ice from the moon or from a near-Earth asteroid and split it into hydrogen and oxygen using solar power, you have rocket fuel. And if you can produce rocket fuel in space rather than launching it from Earth, where it takes enormous additional fuel just to lift the fuel itself out of Earth's gravity well, you transform the economics of space travel entirely. Think of it this way. Right now, every spacecraft that goes beyond Earth carries all of its fuel with it from the start. It is launched fully fueled because there is nowhere to stop and refuel. This is why rockets are mostly fuel by weight. A typical large rocket is roughly 90% propellant and only 10% vehicle and payload. The engineering challenge of getting that enormous mass of fuel off the ground is a large part of why spaceflight is so expensive. But imagine a network of fuel depots in space. Cislunar space, the region between Earth and Moon, as a kind of interplanetary filling station. Spacecraft could launch from Earth with just enough fuel to get to orbit, refuel at a depot supplied by lunar or asteroid-mined water, and then continue on to their destination, the Moon, Mars, an asteroid, wherever. The economics transform. Missions that were previously impossible become possible. The cost of reaching deep space drops dramatically. This vision, often called an in-space propellant economy or a cislunar economy, is the foundation of the most credible near-term business cases for space mining. Not mining precious metals to sell on Earth, mining water to sell to spacecraft. And the customers are not hard to imagine. NASA missions, private crewed spacecraft, satellite operators, space station operators, eventually Mars-bound ships. The market for rocket fuel in space, as space activity grows, could be enormous. And unlike gold and platinum, you cannot crash the price of rocket fuel by supplying too much. Demand would simply grow to absorb the supply. The nations and companies that control the best water ice deposits and develop the technology to extract and deliver that water as propellant will be in an extraordinarily powerful position in the emerging space economy. They will be the Saudi Arabia of space, the Kuwait, the Norway. They will sit on the resource that everyone else needs to get anywhere. That is why the south pole of the moon, with its concentrated water ice deposits, is not just scientifically interesting, it is strategically vital. It is a resource that will power the space economy of the 22nd century. And the race to establish a presence there by the United States, China, India and others is being driven, at least in part, by that understanding. At this point in our journey, it seems worth pausing and asking, when? When does all of this actually happen? When does space mining transition from an interesting idea discussed in documentaries to an actual industry that shapes the world? The honest answer is, no one knows for certain. Timelines in space exploration have a long and undistinguished history of being wildly optimistic. The moon base that was supposed to exist by 1980, predicted confidently in the 1960s, still does not exist today. The human Mars mission that has been 20 years away since the 1980s has not yet materialized. Space is hard, money is finite, politics are fickle, and disasters, both literal and bureaucratic, have a way of derailing even the best-laid plans. With that caveat firmly in place, here is a reasonable, conservative projection of how the coming century might unfold. In the near term, the next 10 to 15 years, the most likely developments are incremental but meaningful. Commercial lunar landers, several of which are already either in development or partially complete, will carry scientific payloads and technology demonstrators to the lunar surface. NASA's Artemis program will land astronauts near the South Pole. Robotic prospecting missions will map the water ice deposits in detail. Smaller companies will continue to develop and test extraction technologies. The first small-scale demonstrations of in-situ resource utilization using lunar regolith to make something useful, extracting water ice in small quantities, will likely occur. These are not revolutionary milestones. They are the quiet, unglamorous groundwork that makes everything else possible. In the medium term, roughly 15 to 50 years from now, the picture grows considerably more exciting. A permanent or semi-permanent human presence on the Moon becomes likely, especially given the pace at which multiple space agencies and private companies are developing the necessary infrastructure. Lunar water extraction, at a scale sufficient to supply modest quantities of propellant, becomes operational. The first crewed Mars missions, whether by NASA, SpaceX, or some combination of actors, likely occur in this window, with a small base established on the Martian surface. Robotic asteroid mining operations, focused primarily on water and volatiles rather than precious metals, become economically viable for the first time. The space economy begins to look like an actual economy. Goods and services exchanged, resources extracted and traded, missions funded by revenue rather than purely by government appropriations. In the longer term, 50 to 100 years out, the transformation becomes genuinely civilizational. If the fusion energy promise of helium-3 is realized, lunar mining becomes a major energy industry. Asteroid mining at scale, including metallic asteroids, becomes possible as robotic technology matures and the in-space infrastructure needed to support it develops. The human population of space, currently hovering at a handful of people aboard the International Space Station, grows to thousands, then tens of thousands. Mars becomes a genuinely inhabited world with a self-sustaining colony capable of growing without constant resupply from Earth. The concept of an Earth-Moon-Mars system, connected by a web of propellant depots and regular transportation, begins to take shape. And beyond that, in the truly long term, a century and more into the future, the possibilities become almost impossible to bound. A solar system-wide civilization, with millions of people living and working across dozens of worlds and habitats, exploiting the resources of asteroids and moons and planetary surfaces. Industries and forms of wealth that we cannot yet name because the materials and products they deal in do not exist yet. A human story that is no longer confined to a single pale blue dot. None of this is guaranteed. All of it requires not just technology, but political will, sustained investment, international cooperation, and a degree of wisdom about how to develop these resources equitably and sustainably. It requires that humanity does not destroy itself in the meantime through war, climate catastrophe, or other means. These are not small requirements, but the direction of the story, the arc of it, is toward the stars. It has been ever since the first human being looked up and wondered what those lights were. Behind every great chapter of human expansion, there are people whose vision seems, at first, completely unhinged from reality. People who describe futures so distant and so different from the present that their contemporaries either laugh at them or ignore them. And then, years or decades later, the world looks back and realizes that those people were not crazy. They were simply early. Let us spend some time with a few of the biggest dreamers in the space mining story. Gerard K. O'Neill was a Princeton physicist who, in the 1970s, published a book called The High Frontier, in which he proposed that humanity's future lay not on other planets but in free-floating space habitats, giant cylinders miles long, rotating to create artificial gravity, housing millions of people in comfortable Earth-like conditions. O'Neill did not envision Mars as the home of the future space civilization. He envisioned vast habitats in space itself, built from the resources of the Moon and asteroids. The math, when he worked it out, was surprisingly favorable. The resources of the asteroid belt alone could support a space civilization orders of magnitude larger than Earth's current population. O'Neill's vision fell out of fashion after the Apollo program ended and NASA's ambitions contracted, but it never went away. Today, it has been revived by a new generation of thinkers, including Jeff Bezos, who has explicitly cited O'Neill as an inspiration for his vision of millions of people living and working in space. Carl Sagan, the beloved astronomer and author, was more cautious about the commercial exploitation of space, but his writing about the long-term future of humanity, particularly in his book Pale Blue Dot, established the philosophical framework that underlies much of space mining motivation. Sagan wrote about the fragility of Earth, about the certainty that Earth will eventually be rendered uninhabitable by the sun's expansion, and about the imperative to become a spacefaring civilization if humanity is to have any long-term future at all. The case for space mining, in its deepest form, is not about money. It is about survival, and Sagan made that case more beautifully than almost anyone. Elon Musk's vision for SpaceX and for Mars colonization is well known enough that it barely needs introduction. What is worth noting is that Musk's Mars plan, whatever one thinks of him as a person, is grounded in a genuine philosophical belief that a single-planet civilization is fragile and that spreading humanity to multiple worlds is the most important thing our species can do. His approach to achieving it, building reusable rockets to drive down launch costs, is not idealism. It is ruthlessly practical engineering. Whether he personally achieves his stated goal of 1 million people on Mars is less important than the fact that his company has changed the economics of spaceflight for everyone. Jeff Bezos and Blue Origin represent a different philosophy. Not Mars as the destination, but Earth's neighborhood as the industrial zone. Bezos has spoken about moving heavy industry off Earth to protect Earth's environment, and about building O'Neill-style habitats as humanity's ultimate home. Blue Origin's New Glenn rocket and its planned Blue Moon lunar lander are steps toward that vision. And beyond the billionaires who get most of the attention, there are hundreds of scientists and engineers whose names you will never see in a headline, working quietly in university labs and small startups and government research centers, solving specific, narrow, essential problems. The person developing a better algorithm for asteroid orbit prediction. The engineer designing a drill bit that works in microgravity. The chemist figuring out how to extract oxygen from lunar regolith more efficiently. The legal scholar writing papers about the international law of space resources. These are the people who actually build the future, step by step and brick by brick, while the visionaries provide the destination. History in the end belongs to both. You need the dreamers to point the direction and inspire the investment. And you need the grinders, the problem solvers, the people who get the details right to actually get there. In the space mining story, both kinds of people are at work. And the combination, slow and uncertain as it seems from inside the present moment, has a way of making the impossible happen. We are nearly at the end of our journey, but before we arrive, let us come back to Earth for a moment. Because for all the cosmic grandeur of what we have been exploring, the most immediately relevant question for most people is a simple one. What does this mean for me? For my life? My children's lives, the world we actually live in? The honest answer is that space mining's most significant effects on Earth may not be the ones that make the headlines. They are likely to be indirect, gradual, and deeply structural. Consider the technology spin-off effect. This is one of the most well-documented and consistent benefits of ambitious space programs. The technologies developed for space exploration have a long history of flowing back into everyday life in unexpected ways. Memory foam was developed for NASA spacecraft. Scratch-resistant lenses were developed by NASA researchers. Water filtration systems on the International Space Station have informed the design of water purification technology on Earth. GPS, which most people could not imagine life without, is a direct outgrowth of satellite technology developed in the space race era. And these are just the most famous examples. The actual number of technologies with roots in space research is enormous. The technologies being developed for space mining, advanced robotics, autonomous systems, in situ resource extraction, additive manufacturing in extreme environments, long-duration energy storage, radiation-hardened electronics will almost certainly generate their own wave of Earth applications. Some of them are already beginning to. The same autonomous systems being developed for asteroid mining robots are being applied to autonomous mining on Earth, making earthly mines safer and more efficient. The same water extraction technologies proposed for the lunar poles are informing better underground water detection on Earth. The cross-pollination between space technology and everyday technology is a constant, ongoing process. More directly, space mining may eventually ease the supply of several materials that are currently sources of significant geopolitical and environmental concern. Cobalt is perhaps the most urgent example. Nearly 70% of the world's cobalt comes from the Democratic Republic of Congo, where its mining has been associated with child labor, conflict, and environmental destruction. Cobalt is essential for the lithium-ion batteries that power electric vehicles and consumer electronics. The transition to clean energy that the world urgently needs is constrained, in part, by cobalt supply. If asteroid mining can provide a supplemental supply of cobalt without the humanitarian and environmental costs of Congolese extraction, the impact on both climate policy and human welfare could be significant. Similar arguments apply to rare earth elements, platinum group metals, and various other materials that are critical for clean energy technology, but whose earthly supplies are concentrated in ways that create fragility and injustice. Space mining does not need to replace earthly mining overnight to have a beneficial effect. Even the credible prospect of space-sourced materials could change the bargaining position of mining-dependent nations and companies, potentially creating pressure for better practices on Earth. And then there is the energy question. If lunar helium-3 can be used as fusion fuel, and if fusion power becomes practical, the implications for Earth's energy system are enormous. Fusion power would be essentially limitless, producing minimal waste and no greenhouse gases. A world with abundant fusion power would look very different from the one we live in today. Energy poverty, which affects hundreds of millions of people, could be eliminated. Carbon emissions from power generation could be eliminated. The geopolitics of energy, which have driven so much human conflict, would be fundamentally restructured. These are enormous ifs, but they are ifs that serious scientists and engineers are working to convert into certainties. The transformation space mining represents is not primarily the transformation of space. It is the transformation of Earth, of what is possible here, of what resources we can access, of what constraints we operate within. The universe, it turns out, is not indifferent to our problems. It has been holding potential solutions in storage in the form of asteroids and moon ice and planetary metals for billions of years, longer than our species has existed, longer than our planet has had land animals. We are simply at last becoming capable of reaching them. We have come a long way tonight, from the hook of a drifting gold-rich asteroid to the legal complexities of space law, from robotic miners in microgravity to diamond rain on ice giants, from the geopolitics of lunar water to the quiet work of the scientists and engineers who are making all of it real. Now it is time for the long view, the deepest frame, the answer to the question that has been underneath all of this: what are we really reaching for? There is a thought experiment that physicists and philosophers sometimes use called the Fermi paradox. The physicist Enrico Fermi, having lunch with colleagues in the 1950s, asked a deceptively simple question. If intelligent life is common in the universe, and if space travel is possible, why have we not seen any evidence of other civilizations? Why is the universe so quiet? Given the age of the universe, nearly 14 billion years, even a civilization that developed only 1 million years before us would have had ample time to spread across the galaxy and make itself known in some way. No one has a definitive answer. There are many possible explanations. Other civilizations exist, but are too far away. They exist, but have chosen to be quiet. They existed, but destroyed themselves. Intelligent life is simply far rarer than we assume. But one interpretation of the Fermi paradox is particularly relevant to our story tonight. It is sometimes called the Great Filter. The idea is that somewhere along the path from simple chemistry to a galaxy-spanning civilization, there is a filter, a step so difficult that almost no species gets past it. Some scientists and thinkers believe that the Great Filter is behind us, that the development of complex multicellular life or of intelligence itself was the improbable step, and that having already crossed it, we may be one of very few civilizations in the galaxy. Others believe more chillingly that the filter is ahead of us, that technological civilizations routinely destroy themselves before they become truly multiplanetary through war, environmental collapse, or some other catastrophe that we have not yet learned to avoid. The space mining story is, in a very deep sense, a story about the Great Filter. A civilization that remains confined to a single planet is, by the logic of the filter, inherently fragile. A large enough asteroid, a supervolcano, a runaway climate disaster, a pandemic, a war, any number of catastrophes could, in principle, end the human story on Earth. The solar system we inhabit offers no shortage of such threats, and yet it also offers, in the form of its unimaginable abundance of resources, the means by which a sufficiently determined and wise civilization could spread itself across multiple worlds, making the extinction of humanity as a whole vastly less likely. Mining is not, in this view, simply an industry. It is not simply a business opportunity, however enormous. It is the first act of a civilization becoming spacefaring. It is the moment when we stop being guests of a single world and begin to be inhabitants of a solar system. Every ton of water extracted from a lunar crater, every ounce of platinum brought back from a metallic asteroid, every structural component 3D printed from Martian iron. These are not just economic transactions. They are steps across a threshold that, once crossed, cannot be uncrossed. They are the beginning of a story whose ending we cannot yet read, and there is something humbling and beautiful in that. We are not at the end of the human story. We are not even at its midpoint. We are, if we are very lucky and very wise, somewhere near its beginning. The universe is old, almost incomprehensibly old, 14 billion years, and life on Earth has existed for about 4 billion of those years. And human civilization, writing, cities, science, art, music, philosophy, has existed for roughly 6,000 years. In the cosmic calendar, we have been here for less than a blink. The solar system we inhabit will remain habitable. We'll have warm sunlight, liquid water, the right temperatures for life for another 5 billion years or so, before the sun expands and makes the inner planets uninhabitable. 5 billion years. The time between now and then is 10 times longer than the entire history of life on Earth. In that time, if we survive and grow and learn, what might we become? What might we build? What might we understand about the universe that we cannot even begin to imagine today? The trillion-dollar space mining industry is not the destination. It is the door that opens onto a corridor that leads to a hall that contains a staircase that goes up and up and up to places and possibilities that no human mind has yet visited. We have the key. We have known how to open the door for decades. We are right now slowly, haltingly, remarkably beginning to turn it. The question is not whether we can. We have already shown in 1,000 ways that we can. The question is whether we will choose to. Whether, as a species, we can find the wisdom and the cooperation and the will to take what the universe is offering us and use it well. History suggests we are not always wise. History also suggests that we are capable, at our best, of extraordinary things. Of going to the moon. Of mapping the human genome. Of building the internet. Of reducing global poverty at rates that would have seemed miraculous a century ago. We are a species of contradictions, capable of tremendous cruelty and tremendous beauty, tremendous selfishness and tremendous generosity. And our future is not fixed. But tonight, in the quiet, in the dark, in the calm space of these hours together, it is worth holding the possibility that the better angels of our nature will win out. That the trillion-dollar industry being born in the darkness above us will be used not just to make a few companies and countries very rich, but to make humanity, as a whole, more capable of surviving, of flourishing, of becoming something worthy of the universe it inhabits. The asteroid with more gold than we have ever mined is still up there, drifting silently in the dark. The water ice at the moon's south pole is still frozen in its ancient craters, waiting patiently. The diamond rain is still falling in the depths of Uranus and Neptune, as it has been falling for billions of years. The universe is patient. It has been waiting for us to arrive for a very long time, and we are at last on our way. Thank you so much for spending this time exploring the cosmos with us. If you made it all the way to the end of this journey, through asteroids and ice moons and legal debates and diamond rain and the long, slow arc of human ambition, that means a great deal. Please like this video if you found it worthwhile, and subscribe to the channel so you never miss a story. There are so many more extraordinary chapters of our universe still to explore, and we would love to explore them with you. Until next time, sleep well, dream big, and remember that the stars are not as far away as they used to be.